One of the theoretical foundations of using deep learning in applied work is this Kolmogorov-Arnold result, which was proved in late 50s of the last century by Kolmogorov and his student Vladimir Arnold. And the result says the following. If you have a very complex function, essentially what is deep learning? Deep learning is just a very complex function. You want to generate prediction y, and you have this very complex function f that takes input x, and this function is given by a deep learning model. It basically can be written using mathematical formulas, the same way we were able to write generalized linear model, logistic regression, or linear model. And the mathematical formula was again derived by Kolmogorov and Arnold, and it has the following form. So you take input x, okay, and then you apply this function f, and this is index L here. This is L function, and this function has parameters WL and BL. And here is the form of this function. So here's how this function looks like. It is first what it does what you guys have seen before. It essentially looks like a linear model. So it takes an input and it does what linear model would do. You have a bias, and then you have what is called weights. And weights are essentially equivalents of beta coefficients in the linear model. But then once you did this transformation is called linear or affine transformation, then you apply some nonlinear function after that. Nonlinear function. And this function is called activation function. All right, so you take input x, then you do a linear model type transformation to it, and then you apply some nonlinear function to it, which is called activation function, which is very simple. And we're going to look at a few different forms of this activation function. And then what you do, you take output from this function, and then you use it as an input to function fl-1. And fl-1 has exactly the same form. It has linear model type of transformation following by a simple activation function, and you keep doing this L times. So, and that's what this stands for. So you essentially do L transformations to your data set or to your input. And when the number of transformations, the number you process this input, is large. When L is large, we call it a deep model, meaning that you have to go through many layers. So the number of the layers is large, meaning that the network is deep. So when L is large, we call it deep learning. So that's what it is, essentially. That's the mathematical form of deep learning. There is nothing that you haven't seen before. You've seen this linear model type transformation, then you do some nonlinear. And essentially, if you think of logistic regression does the same thing. It does the linear model type of transformation to the input, and then it applies the logistic function to it to get the 0-1 output. This is very similar. But in deep learning, you just do it multiple times. So you take the output of this transformation and then send it to another one, and it's of the same type, and you keep doing it many times. And then whatever the output you generate at the end is your prediction. That's it. So here is a more unrolled version of the deep learning model. So what do? You take your input x, and then you do this linear model type of transformation. So bias times the weighted sum of the inputs, and then you apply this function, activation function, to produce what is called hidden output. So this vector z is called hidden output. And then you take this Z output from the previous layer and use as an input in the next layer. So, and you do the same thing. You do linear model type of transformation applied by nonlinear function to generate one more hidden output, and then you take this output and you use it as an input in the next layer, and you keep doing this until you do the last layer. And in the last layer here, in this example, we solve the regression problem. And in the regression problem, as I said, in the last layer, you just do linear regression. But now you do linear regression not on the original inputs X, but you do it on this ZL, which is the output, the hidden output of the previous layer, the Lth layer of your model. And essentially, you can think of this ZL, the one used in your linear model, is a lower dimensional representation of input X. So let's think what this low dimensional representation might mean in terms of the images. Let's say I have an image, okay, and let's say my image has a car. Okay, I don't really know how to draw a car, but okay. And the low dimensional representation of this image might be, so it has two wheels, car body. So essentially, just knowing that the image has two wheels and a car body is enough to say that this is image of a car. So if you try to predict which object is showing on the image, and then just knowing those two facts about the image allows you to say what's on the image. And you can think of those two facts being low dimensional representation of this image. Instead of knowing what exactly is on each pixel, you simply try to deduce those two simple pieces of information from the set of the pixels. And once you know that, then you just plug this into linear model or logistic regression, and the logistic regression will say, yeah, it's a car. That's overall view. And here I give you a link to the TensorFlow webpage where you can play with different configurations of neural networks trying to predict the classification and regression for some complex data sets. And I want to use this slide to mention two major software libraries that are used for deep learning nowadays. It is a TensorFlow developed by Google, and PyTorch, which was originally developed by other company, but now Facebook is the company that maintains this library. Both of them, so PyTorch is, you can judge from the Py here, is developed in Python. And TensorFlow originally was developed in C++, but it mainly used in Python. You can call C++ functions from Python. So essentially, if you know how to use Python, you will have access to those two major libraries. And if you don't know how to use Python and you only use R, so for R users, there is a library called Keras, and essentially it's a higher level version of TensorFlow. So essentially you can use TensorFlow if you are an R user. Let's do a quick example and compare the prediction of tree models with deep learning models. You remember, tree model is just trying to split the space into regions, which are squares if you are in two-dimensional input space. And we're going to look at classification problem. So we want to classify red circle versus green. So we have two classes, red is 0 and green is 1. So that's a classification problem. And what you see here, we have three data sets. So we have simple data set, we have a circle data set, and we have spiral data set. And you see how well tree does on all three data sets. So tree does very well on the simple data set. So it finds how to split, it basically splits the region like this. So it is able to isolate the red points from the green points relatively easy. And the neural network, so this is tree model here in the upper row, and this is deep learning model in the lower row. And deep learning model essentially does the same. It is able to split and separate the red dots from the green dots. Now the circle data set tree model does pretty well as well. So it just draws a square around the green dots and is able to isolate them. So it does prediction very well. And the deep learning model does well on this task. However, the moment you start getting a little bit more complicated of a data set, like this spiral, then this simple splitting into squares doesn't work anymore. So here you see example of how tree model tries to do the splitting. So it does this region here, and this region here, and this region here. So although it does relatively well, and you have mostly regions with one color, but it has some spillovers, like this region will have both red and green, and it has to do a lot of the regions to do this. So the model becomes very complicated, and it's not good. We know that model complicated is not good for prediction. And deep learning, you can see the geometry of the deep learning separation. It's much more closer to the nature of the data set. So deep learning is basically tries to identify the region that has a spiral shape compared to trying to fit those square regions into the data. So here the deep learning does very well, and I would say tree model doesn't do that well. So it gives you a sense of flexibility. Essentially, you can think of deep learning as a way to split the region into subregions, but instead of using the lines, drawing the squares in the input region, deep learning model can do much more sophisticated and more complex geometries. So it can have a spiral geometry. And this flexibility allows deep learning to be much more efficient when the data set is complex. So here's example of one layer of deep learning. Essentially what it does, each part of the layer draws a line, okay? And so you have multiple lines, and essentially on each layer, deep learning splits your region using those lines. So one distinction between the deep learning and trees is that DL uses lines, and it can be diagonal lines, and tree uses horizontal or vertical lines. So that's one distinction. Just to begin with, deep learning has more complex way of splitting your input space. But the next distinction is that deep learning can combine those things. So meaning that on the first layer, it will split your region using the lines. But on the next layer, it can combine those subregions. Meaning that if you have two triangles on the first layer, triangle like this and triangle like this, so this is first layer of deep learning. On the second layer, it can have a combination of those triangles. So the geometry can be basically, if point is here or here, then the point can be classified in a given way. So combining those simple geometries into more complex ones gives the rise to very complex shapes and patterns that deep neural network can fit into. Let's talk about the specific application, the image processing. And there are many driving factors for that. One of those driving factors is the ability of processing. The GPU and TPU are two types of processors that are very efficient when processing structured matrix data like an image. And we also have large data sets, which are called benchmark data sets. So scientists who work in this field of image processing have data sets available to them that they can play with, and a lot of people spend a lot of time playing with those benchmark data sets and developing new deep learning models, trying to do the tasks of prediction, for example, of an object on an image. So here's example of the performance of image recognition, and you can see the evolution in 2011. The task of predicting a label of an image or trying to identify an object shown in the image, the machines would have 26% error compared to the 5% error of the human, and in 2016 this went to 3% error. So machines are becoming more powerful than humans, and we'll have a couple real-life applications where we see when machines actually outperform humans when image classification is done. I'm going to show you a very simple example of how to do image classification using R, and we're going to use Keras library to do that. Here's the data set. It's basically a data set of handwritten digits, and it was originated by Jan LeCun. His task was to analyze handwritten digits in the zip codes on the envelopes. So postal office can take an envelope and then look at the zip code and automatically process the zip code, so the sorting can be done automatically instead of human sorting. And essentially that's how these postal offices do that. It's automated sorting. And so there are 60,000 images, and each image will be one of the digits. So we have a bunch of different zeros, bunch of different ones, and each image will be what is called labeled. So for each image we know this is 0, this is 0, and this is 0. We know exactly which label associated with this image. Now the task is to use this set of images and labels associated with those images to do the task of prediction. So when we see a new envelope, we'll look at the set of 5 digits in this envelope, and we want to recognize them and predict what is the zip code associated with this envelope. And you can see that this was a benchmark task. This data set of digits is called MNIST data set, and it has been used as a benchmark for many years. It is actually still used as a benchmark for some of the research projects. And you can see that in 2013, the top model had 0.2% error. So just think about this. Error rate was 0.21%. So out of 1,000 images, only 2 images will be incorrectly classified. And this is 2013. So those are early days of neural networks. And here's the architecture of the neural network model that we're going to use. So we're gonna start with input X, and we're gonna do the linear model type of transformation on this input X, and then we're gonna use this function which is called ReLU. This is our activation function, and ReLU has the following shape. It's basically 0 if input is less than 0, and it's just input itself if input is greater than 0. So that's as simple as that. So that's X, and that's ReLU of X, which is just max of X and 0. That's it. It's a very simple function. And so we just use this ReLU function to follow this linear transformation here. And another thing we're going to use here is this called dropout. So what happens in this task, we start by an image, which is, so our input X is 28 by 28 image. Okay, and essentially what we do, we vectorize it. And so we have this long vector of pixels, which has dimensionality 28 times 28. And then, instead of using all of the pixels, we actually randomly remove half of them, which seems like a strange thing to do. So we just remove half of the pixels. And then we use this randomly selected fraction of the pixels as an input. Okay, and then we do this transformation. So we do this, so that's our X. and then we do this transformation. We apply this weight to this x. Actually, we call it y. So we apply this, we call it y1. So that's the result of removing some of the inputs. And then we take this y1 and we apply this w1, y1 plus b. And then we apply this max, this one and 0 function to it. And this will generate what is called z1. So we're going to move to here, z1. And then we actually repeat this process. We randomly remove some of the entries from z1. And then we remove some. We call it y2. And we removed some entries. And the result is this vector called y2. And then again, we're going to do the same transformation. So our Rayleigh function, w2, y2 plus b. And the output of this is going to be called z2. And we just keep doing this one more time. And at the end, we use this function softmax, which is just logistic regression with multiple classes. So softmax does logistic regression with multiple classes. You remember we talked about when you have more than 2 classes, essentially you have, if you have k classes or labels in your data set. And in this MNIST case, we have k equals to 10. We have digits 0 through 9. So each of those digits will have one of those labels. And then we essentially do k minus 1 logistic regression. That's what softmax does k minus 1 logistic regressions. That's all it is. So in the end, we just do logistic regression on this low dimensional representation, which is in this case y3 of the original input x. Okay. Here's the code how it can be done in R. So we load library keras, and then the keras has this MNIST dataset built in. So we just take it from the library and we split the dataset into the training. So we have X training and Y training and the test dataset. And then we need to do this to categorical, meaning that we want to convert this one to discrete variable. We want to specify that Y is just a label between 0 and 9, so 10 different labels are possible. We do it for train and test data set. And then what we do here, we call this vectorization operation. So essentially we take the matrix and we vectorize it. So we write a long vector. So we start with first column, and then we take the second column and append it to the bottom, third column appended, and we keep appending those columns before we run out of columns. So this operation does this. It's vectorization. Convert, this is convert matrix to vector. And then we rescale them. So remember that each pixel has this intensity of the black from 0 to 255. We rescale it so each number is between 0 and 1. So just divide by 255. And that's it. Now we are ready to build the model. So we're going to use this sequential model. Sequential means that the layers come in a sequence. And we start with what is called a dense layer. And this dense layer takes input with dimensionality 784. So this is a vectorized version of the image. And it has 256. So the output is going to be 256 dimensional vector. We have 784, so we're going to be talking about dimensionalities here. And in the first layer, we take 256, and then we take a dropout. So out of those 256, 40% will be zeroed out. So we just set them to 0. And then again, we apply another layer, and the output of this layer has dimensionality 128. And 1/3 of the entries from this layer will be zeroed out again. And then we just take this 128 and we put it to logistic regression to predict one of the 10 classes, and output of the logistic regression is a label 1, 0, 1, all the way to 9. So that's how this model works. And summary of the model will basically give you the outline of the model, what happens in each layer in terms of dimensions. It also will tell you the number of the parameters. So you see the number of parameters is quite large here. And then we're prepared to train the model. So we just say compile first, and then feed is the function to train the model on the data set. And once we did this training, we are ready to do the prediction. And we use these predict classes. We give the text data set, and we get this y hat. And we print the first 5 entries, 6, 5, 8, 6, 4. And if you plot the history of the training, you will see that it's an iterative process that uses to estimate the weights of the neural network. And by the end of this training process, after 15 iterations, we reach this accuracy at around 98% accurate. So if you think about it, it's a relatively simple neural network model with just 3 layers. And we do vectorization, so there's nothing fancy. And even this very simple architecture allows us to do very accurate prediction of the labels. And if you want, you can go and compare it with logistic regression. So don't do any neural network. So just take each pixel as an input and try to do logistic regression. You'll see that you won't be able to get that level of accuracy without doing this pre-processing or doing these dimensionality reduction steps of neural networks. So example of image classification, we watch this hot dog not hot dog video. You can watch it again here. So here are a few examples of the image classification. Cucumber sorter. It was a Japanese farmer who saw his parents manually sorting the cucumbers, and you have to sort them according to the size. So he came up with this machine learning based approach where he has a camera overhanging the sorting table, and then he developed this mechanical arm that takes a pickle and shuffles it into one of the, I think it's 5 different boxes depending on the size. So the camera looks at the cucumber, tries to classify what size the cucumber is, 0 through 4, and then once it says 3, for example, it gives the command to the shuffle hand to put it into the bin associated with this class. So this and the person who designed it, he didn't have any training, so it gives you an idea that using the libraries like TensorFlow or PyTorch is relatively straightforward, and you don't really have to be computer expert. A lot of things you can actually do following examples from the web. Toilet paper assignment in the Table of Heaven in Beijing when they try to track when toilet paper runs out, identification of untagged friends on Facebook. If you have ever seen this feature, when you upload an image, Facebook tells you, oh, maybe that's one of your friends, and actually tries to suggest which of the friends it is. It's a classification algorithm, so it takes all of your friends and tries to classify which of them is shown in the image. Detection of collision between subatomic particles in CERN. We talked about Higgs boson discovery a few lectures ago, and nowadays image processing techniques are used to analyze the trajectories that come from the detectors. So it's used both in science, and it's used in industry, and it's used in farming actually quite a lot now. A lot of the monitoring, plant monitoring nowadays is done using image processing. And when you try to monitor your fields, you actually would use images from the satellites. People try to identify the problems with irrigation, problems with disease, problems with insects, and instead of going in manually or with human looking at those fields, you can just take the satellite images, run it through the machine learning algorithms. The machine learning algorithm tries to predict whether any problems with your crops. So here is description of the Japanese cucumber example. Another example, AI helps to understand and protect snow leopards. Problem of tracking snow leopards is not an easy one. Those are hard to tag, usually tag and used to track the population. But in this case, scientists came up with this approach where you had the network of cameras in the mountains. And whenever a leopard was detected by the camera, the pattern on the skin would be used to identify which leopard it is. So instead of using the tags, you can track your leopards by just detecting the skin patterns and matching them one with another. L'Oreal has AI-powered skin diagnostics. You just take a picture of yourself, you upload it to the app, and they try to decide whether some treatments need to be done to your skin.